Chapter 10, Lesson 4. In this lesson we'll talk about two important concepts. First, the density of gases, and then we'll talk about the molar masses of gases, which are related to the density. Now, both of these concepts will actually draw on our discussion previously of the famous gas law equation PV equals nRT. So really, these two concepts are an extension of PV equals nRT. Now, it turns out that the density of anything defined is mass over volume. So what we could do is we can ask, what is the density of carbon dioxide gas at certain conditions? And it turns out that we can actually calculate the density of any gas as long as we know what the gas is theoretically, which is neat because then we can go on and measure the density of that gas and we'll come up with the right answer. So if we take a look at carbon dioxide gas, what we'll do in all cases when we use the PV-nRT equation is we will assume we have 1 mole of a gas. If we assume that we have more, then as long as we follow the rules, we'll get the right answer. But it's easiest to assume that we have 1 mole of that gas. And then the reason we do that is because moles are connected to grams. And this will be important. In order for us to find out density, we need mass, which is in grams. And the mass is connected to moles, which comes from the PV-nRT equation here. So it's all connected, as you can see. We're going to derive for you the equation. Now, if you don't understand this derivation, it's not necessarily, it won't necessarily hurt you, but it's a good idea to see where we come up with the density version of the PV equals nRT equation. First, we take PV-nRT, which is this, just flipped around, and we rearrange it by moving volume to this side and by moving R and T to this side. And notice we'll have to divide it in both cases. Next, we define something called molecular mass. This technically is what comes from the periodic table. The molecular mass of anything is the mass of that anything divided by the moles of that anything. So it's mass per mole. What we do then is we move the moles over to this side, and the reason we do this is because we want to now plug this into our PV equals nRT equation from up above, from here essentially. And what we do is we multiply essentially every side of this equation by this idea here. So what we do is we take m. We take both of these portions. I'm actually going to erase so it's easier to see. We take a big M and multiply it by the right side of the equation, and then mass over moles, we multiply that by the left side of the equation. And what happens is, since we have moles on the bottom here and we had moles on top from the ideal gas law equation, both of these actually cancel out. What we're left with is mass and volume on the bottom from the ideal gas law equation, and this is what gives you density. So here is where this comes from. Again, if this doesn't make too much sense how you rearranged, don't worry, just as long as you see what the equation looks like in finality. And here it is: the density of any gas equals the pressure of that gas multiplied by the molecular mass of the gas. This, remember, is grams per mole from the periodic table. Divided by R and T. And here it says that one only needs to know the molecular mass, the pressure, and temperature to calculate the density. So we can theoretically calculate the density of any gas under any conditions. This is a pretty powerful tool. So why don't we try one of these? This one says, what is the density of carbon dioxide gas at standard temperature and pressure, at STP? If you recall, STP is a set of conditions where we have 0 degrees Celsius and 1 atmosphere under these conditions. And so to calculate the density of carbon dioxide gas, we can go ahead and employ our equation, the rearranged equation. Density equals PM over RT. So if we just plug and chug, it looks like our temperature must be in Kelvin, so that's 273 Kelvin. Looks like our pressure is fine. Remember, all this is based on the value R of 0.0821 liters atmospheres mole Kelvin. So looks like our atmospheres are good. Our molar mass, big M, of carbon dioxide gas is simply, we'll take carbon, which is 12.01 from the periodic table. We'll take two oxygens, each of which is 16 grams from the periodic table, and we get the famous number of 44.01. So the molar mass is 44.01 grams per mole. And the rest of it is just plugging into the equation. So the density of any gas will be the pressure, which is 1 atm, multiplied by the molar mass, 44.01 grams per mole, divided by R, which is 0.0821 liters atmospheres, over mole Kelvin, multiplied finally by the temperature, which is 273. And actually, why don't we take a look at the units. If we've set everything up right, the units should cancel out, and what we should be left with is the units of density, which, remember, is mass over volume. So looking at the equation here, looks like atmospheres cancels out, looks like Kelvin cancels out, looks like moles cancels out. We're left with grams and liters, which essentially, usually the density of gases are reported in grams per liter, because the solids and liquids are reported in grams per milliliter, but because gases are so much more rare, they're reported in grams per liter. So if you plug all these numbers in, we got 44.01 divided by 0.0821 and 273. We should get ourselves a final value of 1.96 grams per liter for carbon dioxide gas. Now I realize that what we're using is the number of significant figures isn't indicated, but standard temperature and pressure essentially give us exact values of 0. So when we say 0 degrees Celsius, we mean really 0.00, really in a precise manner. And same thing for atmospheres. So in this case, really, we're limited probably by either temperature or not temperature, but either by the R value or our molar mass value. In this case, I think we're justified in putting down three significant figures: 1.96 grams per liter for the density of carbon dioxide gas. And this is experimentally verified quite easily. You can measure a liter of gas, you can weigh it and find out exactly how much it weighs, and you can verify this quite easily. The second concept that we'll work with then is the molecular mass or molar mass. This is essentially, we'll take the density equation that we just used and rearrange it for molar mass. It's nice that the molar mass is already in that density equation. So what we do is we rearrange it by multiplying by R, multiplying by T, and then dividing by P. And that's essentially what we got here. Now this equation then can be used to find the molar mass of any gas. Now, this is extremely important because the molar mass of any substance is very important. In order to identify what a substance is, say if you produced a new known substance, you want to know its molar mass. So then you can go on and identify what it is. Well, that's done usually by using the ideal gas law. So the ideal gas law is indispensable, extremely important to give us the properties of any substance, because technically any substance can become any solid, even if the substance is a solid. We can make it into a liquid, we can make it into a gas, and then using this equation we can determine its molar mass. Very powerful. So we're that came up. So we're going to, why don't we do this little problem. This problem will also be a bit involved. So let's see if we can make sense of it before we work it out. A large flask is evacuated and found to weigh yay much. It is then filled with a gas to a pressure of 735 torr at 31 degrees Celsius and then re-weighed. Its mass is now a little higher, 137,456. Finally, the flask is filled with water at 31 degrees Celsius and found to weigh yay much. And then the density of water at this temperature is very close to 1, a little lower, and then calculate the molar mass of the unknown gas. Now, it does give us, it looks like, a lot of information that we may not see right away the need for. Now, recall our equation that we're using is the density equals, well, we've rearranged this equation, so essentially we're using the equation of molar mass equals density times RT divided by P. Now, the temperature is given to us. That's easy enough to find. The R is a known value. The pressure is also given to us. Our only issue here is to find the density. And essentially the density, remember, is grams per mole of the gas. The density is grams per liter of the gas. So what we'll have to do is, the grams is easier to find, but the volume of the vessel will be harder to find, and that's all this business about filling up with water and then emptying it again. So we'll have to essentially work on finding the density. That's essentially the toughest part of this. So why don't we do that on the next page. So to find the density of this gas, what we'll do is we'll have to get grams and liters. Now if you take a look, the flask was first weighed, so we have say an empty flask. Kind of looks like a flask. And this flask weighs 134.567 grams, and then it's filled with a gas. So the same flask then is filled with a bunch of our gas that we're measuring, and then it's found to weigh 137.456. After this, it is then weighed, emptied again, and essentially filled with water completely. So it's quite a bit heavier now, and this mass is 1,067.9 grams. This is also grams. So the mass in this case will come from the difference of these two. This will give us the mass. So difference, if you subtract these two values, what we'll find is that we have around 3 grams or so of the gas. Let's go and do this precisely. 137.456 minus 134.567. So we have 2.889 grams. Now this will give us the grams portion of it. To get the liters, what we'll have of this flask, we're not given the liters directly. What we'll have to do is we'll essentially have to use the density of water to get the liters. So we're actually using a little density trick. So if we take, we know that the density of water, we were given the density of water as 0.997 and grams per. This is grams per milliliter. So we can use this then and use the mass. If we subtract these two values, if you take the difference between these two, what we'll find is that the mass of our water is around 800 or 900. So let's go and subtract those two. 1067.9 minus 134.567. So our mass of our water will equal 933.3 grams. We could now use the density of water and the mass to find the volume. Density is mass over volume, so the volume, if we rearrange this, the volume goes this way and the density goes back down. So we got volume equals mass over density. So to find the volume then of the water, we simply plug the mass, which is 933.3 grams, divided by the density, 0.997 grams per mil, and we will get our volume, which would be 933.3 divided by 0.997, 936.1 milliliters. This is our volume now. So we're close to our equation being fulfilled. Technically, since we want liters, the volume then would equal, if you divide it by 1,000, you get yourself 0.9361 liters. We are now ready to plug all our values into the molar mass equation, which we recall was molar mass equals density RT divided by pressure. So let's go ahead and plug everything in, and then we can find our molar mass finally. So the density in this case would be the mass divided by the liters. We can do that separately, or we can put it directly in. So actually, let's go ahead and do it separately here, right above here. It looks like it is, we got 933.3. Sorry, no, that's not the value. Let's try that again. The mass that we're going to have to take account of, because this is the density of the gas, so this will be the mass and this will be the volume in liters. So our density, we'll squeeze this up in here, is 2.889 divided by 0.936, and this gives us a density of 2.889 by 0.936, a density of 3.0865 grams per liter. This is what we'll plug into here. Okay, so once we've determined that, let's go and plug and chug the rest of it. So 3.0865 grams per liter multiplied by the gas constant, 0.0821 liters atmospheres mole Kelvin, multiplied by our temperature, which in this case, if you look back at the problem, is 31 degrees Celsius, which means we have 304 Kelvin. So we are getting a bit tight in here. All divided by our pressure, which is given to us as 735 torr, but recall that we have to be in atmosphere, so we can actually just convert it directly in here. This is a little trick that you can do, divided by 760 torr, and this will ensure that we got ourselves in 8 atmospheres. So what we now have to do is plug and chug. So let's go ahead and do 3.0865 multiplied by 0.0821 multiplied by 304 divided by 735 and then over 760, and we should get ourselves a molar mass of 79.65. If you analyze the units, what you'll see is that the liters cancel out, the Kelvin cancels out, the atmospheres cancel out, and you're left with grams per mole, and that's exactly what the units of molar mass should be. So we got 79.65 grams per mole. Looks like, according to the significant figures, we are probably justified in using 3 significant figures as it stands. So how about we say 79.7 grams per mole for our final answer. And this here, after some toiling, we found the molar mass of this gas. Very important piece of information about a substance. And finally, before we finish the lecture today, we're going to mention that really what we've been doing is something called the Dumas method for determining the molecular mass. Now, it's pronounced Dumas, although some college students use a different pronunciation for this term. Make sure you use the correct one. And what we essentially do is we're able to determine the molecular mass of a substance by setting up an experiment like this. It is quite a simple experiment. You take a bulb, essentially, and you fill it with your unknown. And the unknown can be a liquid. It could even, if you're careful enough, be a solid. Now, since you're going to be using boiling water, most of the time it's going to be a liquid. So that way it can evaporate in the boiling water. And as it evaporates, essentially it fills this little bulb with your gas, with the vapor phase of your gas. All the rest of the vapor essentially kind of leaves out of it. So first, you by heating it up, you ensure that this whole thing is filled with your gas. And then what you do is you take it out after it's been boiling for a while. You take it out, you carefully dry it, and then as you take it out and cool it, all the vapor actually condenses as liquid down at the bottom. You can then weigh this, and then since you got the mass, this gives you grams. And you can then determine the conditions under which this happened. You can find out the volume of your flask. You can find out the temperature at which this happened. And this is essentially at the boiling point of water. You can find out the pressure at which this happened, and notice you'll have all the necessary details to get you the molar mass based on the equation that we just saw. Density multiplied by RT divided by P. And this is called the Dumas method of determining the molar mass of a gas, and a very important idea in chemistry. And this concludes lesson 4 of chapter 10.